Okay, so so thanks all for coming. End of the semester and all that, but still, well, you made it. And thanks to Avi for arranging this while he was still in Malaysia. Uh, so yeah, matching is really well. It is a very central problem in the theory of algorithms. And it has an amazingly beautiful, remarkable, deep structure. And here is a quote from the great book of Lowas and Plummer on matching theory that really is quite illustrative. How do I? Oh yeah, here. Oh, no. Yeah. Okay. So he says. Matching theory serves as an archetypal example of how a well-solvable problem can be studied. And the reasons that he gives are graph theoretic, the fact that it gave rise to so many important ideas in graph theory. And if you look at the theory of algorithms, I think this is even more true in much bigger ways. So it has given rise to many powerful tools in algorithmic theory. Polyhedral combinatorics, how to characterize the facets of polyhedra, which was important for many reasons. The canonical path argument for proving expansion of the underlying graph of a Markov chain, and then therefore all the work that got done on MC method, the isolating lemma, and it goes on and on. I mean, if you look at online algorithms, whether you look at probabilistic analysis, whether you look at parallel algorithms, I mean, everywhere it gave rise to really beautiful techniques. And not only techniques, but entire paradigms. The primal dual paradigm, which had huge impact in exact approximation, and now even in the solution of nonlinear convex programs, came from matching. Edmunds defined the notion of polynomial time solvability in matching. Valiant defined the notion of sharp P in matching. And in this result, we got the equivalence of random generation and approximate counting for self-reducible problems. And that lies at the core of this entire area of MC method. So, I mean, it's really quite remarkable how much the study of matching has contributed to the theory of algorithms. I mean, at least in this talk, I'll give you a small glimpse of the great structure that this problem has to offer. Oh yeah, game theory and economics. Again, the Nobel Prize-winning stable matching work, Shapley-Shubik's work on matching markets, and in the internet age, the AdWords market, which is really a takeoff on online bipartite matching, multi-billion-dollar. I mean, in those days when we did the KVV work, there was no dollar signs attached to the problem, but now there are. Anyway, goes on. So here, as I said, I'll assume the basics and move on. So this is the basic schema for finding a maximum matching. Start with the empty matching, find an augmenting path, augment until there are no more augmenting paths, and then it'll be a maximum. And clearly, you'll need order n iterations, order m per iteration, so order m n time. So no. General, huh? Sorry? This is for general graphs, right? So the question is can we improve the running time? Oh, you didn't read my abstract? I said I will assume an augmenting path. I will come to that in a moment. So an augmenting path is an alternating path. So with respect to a matching M, an alternating path, which is alternately matched and unmatched edges, and it goes between two unmatched vertices. Okay, and I'll illustrate it also in a moment. So, so how do you improve on it? Well, do you really need order m time per iteration? Let's see this through a slightly changed scheme where
so
we.
M is the number of edges.
Yeah, m is the number of edges and n is the number of vertices. Yeah. So now we are going to find shortest paths in each iteration, not just any ordered path, but shortest paths. Let's see how that works. It turns out that the length will be non-decreasing. So you'll get some paths of length 1, of course, first, which will just be trivial work to match them off and to find them, and then maybe 3, then 5, maybe, and some lengths may be skipped. Now, if you look at, now you see that that's an augmenting path, right? It goes, and I'll show you in a real graph also.
So your red dots are current
match. Exactly. Sorry, yeah, I should always specify this. These are the current matched edges, and these are the unmatched edges. And these big blobs are the unmatched vertices, and you can imagine where the matched vertices are, namely here, and so on, right? Now, here's a very interesting property. If you look at the matching at the end of this augmentation, okay, M, then all of these paths are actually disjoint with respect to M itself. So certainly this, so this is an augmenting path with respect to M. This is an augmenting path with respect to M augmented with this matching, right? But because it's disjoint from this, it's also an augmenting path with respect to M itself, and so on. So all these of the same length are all disjoint augmenting paths with respect to this matching, okay? And this is a maximal set of disjoint minimum length augmenting paths. You cannot have another 3-length path, because you would have found it in this scheme. The next one would have been if there was a disjoint 3-length path, you would have found it, right? So what you have found here is a maximal set of disjoint minimum length augmenting paths.
So this requires proof that
Yeah. All this requires small proofs. These are tiny proofs, yeah. Okay. Yes, coming up. So an augmenting path is a simple path that consists alternately of matched and unmatched edges and goes between two unmatched vertices. So this is an this is an augmenting path, right? 3-length augmenting path. I can probably find, yeah, here is
on the bottom.
Yeah, here, boom, 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 boom is another augmenting path, right? Simple path, alternately matched and unmatched edges, and going between unmatched vertices. And the importance is that if we flip unmatched and matched edges on this, we get a valid matching of one higher cardinality, obviously, right? And that's why this the very first slide is a good way to find a maximum matching. You have to give proof that when there are no more augmenting paths, you are done. No matter how you got to this matching, it will be maximum. All those are very easy proofs, actually. But take it from me, because we'll go to, a different world in a moment. So this is our new scheme, okay? Find a maximal set of disjoint minimum length augmenting paths in each phase, and we'll call it a phase, okay? Right? They're all disjoint. And the question is, how fast can you do this? I mean, maybe you don't have to spend as much time as E times the number of paths. Maybe you can do it in E or M, right? Maybe you can do it in M itself, right? That's the hope. And indeed, in bipartite graphs, you can find it in M per phase. And there's a proof, simple proof, very simple again, that only square root n phases suffice, even in general graphs. Is that okay?
So that's also
and also Karzanov at the same time across.
So you can find the set of maximal disjoint minimum length augmenting path in
order m time
linear time, and
in bipartite graphs.
If you just iterate this,
Yeah.
you will finish in root n time.
Time. Yeah. Is that okay? Everybody's on? Yes, sir? You're completely okay. Great, thanks. So the question at this point was, can you do this for general graphs, right? And in 1980, Silvio Micali and I produced this paper that said, yeah, we can do it, and it was in Fox 1980. But no proofs were given at all. And then in 1989, I gave a paper which had a complete proof. And I realized that there's one aspect of the thing that couldn't be proven, and I will show you what that exact statement is later. But as a result, to get order m per phase, we do need a result of Gabor and Tarjan, which actually came later. Okay, but if you don't use this result, then you can use Tarjan's union find algorithm, and that will multiply this by an inverse Ackermann function, which is at most 4 if the number of edges is the number of molecules in the universe. But it's not linear time, so we're not happy with that level of inefficiency, right? So anyway, so that's where things are. And this year I've given quite a simpler proof, new paper, and also readable finally. So and actually it was Bob Tarjan who sort of initiated this round of talks and my writing this new paper. And he was supposed to be here, but had some very important urgent business at the last moment. But anyway.
There was another paper that had a simple proof of, I forget the
Norbert Bloom. Norbert Bloom.
Right.
It was a variant on the same algorithm, okay? And it doesn't have all the proofs that I'm going to show you, which I think are.
It was a complete.
Well, I mean, there.
When you wink like this, you have to refer to Micali-Vazirani.
Sorry, I'm saying that there are proofs and there are proofs. Okay. At the end of this talk, maybe we can get to that statement. Okay.
But anyway, there was another paper.
There are many people who have. I mean, Gabor Tarjan had another paper, apparently giving a proof. I mean, there are many people who wanted to prove it, but let's talk about that after this talk, because you'll see what the real status of the proof is and what it takes, because it takes. Okay. And I really appreciate this because you'll see. I mean, you'll see what it takes. I mean, it really takes something. Okay, I'll make a statement about what it takes also, in very explicitly, in a moment. Let's start with the bipartite case, because I want to pick up a couple of very interesting ideas, algorithmic ideas, which I'll extend to general graphs. So you have a bipartite graph with bipartition UV, E is the edges, and let M be the current matching in it. And with respect to that, let's define the level of a vertex to be the length of the shortest alternating path from an unmatched vertex, any, to V. Okay? And like here, the level of this unmatched vertices on the U side will be 0, right? This guy will have level 1, this guy will have level 2, this guy will have level 1 also because of this guy, right? Right? So level is the length of the shortest alternating path from an unmatched vertex to V. And the smallest number that we have on an unmatched vertex here will be the length of the shortest augmenting path, obviously.
So you could run from V a breadth first search.
You could run from all the unmatched vertices here.
From simultaneously.
Simultaneously. Yeah, exactly, until you reach all vertices that you want to. Okay, so an alternating breadth first search starting from all unmatched vertices on the U side will do it. And so at search level I, you look for guys that should get level I plus 1 and so on. And on this, okay, on a bipartite graph, it works like this. You start with unmatched vertices on U. This is not exactly that graph. You look for unmatched edges incident and give these guys level 1. You look at their matched neighbors and give these guys level 2, and so on. And one more thing you do, which is very important, is that each time you find an edge, you like this edge, you note this as a set in its set of predecessors. Okay, so this guy has 2 predecessors, A and B, and you can do that in constant time per edge, right? And you go on like this. Can such an edge happen? Not in bipartite. It creates an odd cycle. What about this edge? It's only going from the U side to the V side, so surely that can happen. But it's useless, because why would you go like this when you can go like this if you want to find a shortest augmenting path, right? So this is not needed. And then whenever at some level you will hit the unmatched vertices on the V side, you stop there, you forget about these guys. And now you pick any unmatched vertex on the V side and take predecessors, and you are guaranteed to find predecessors all the way to an unmatched vertex on the U side, and that will give you an augmenting path.
You
Aug-
also find maximal disjoint augmenting.
we're coming to that. We are going to that. Yeah. So augment there, remove this path altogether, all the vertices, and all the edges incident at these vertices. Okay, obviously, remove it altogether. And now, look, this guy has no more predecessors. If you came down here, you will never be able to go all the way to an unmatched vertex. So remove this guy, then this has no more predecessors. Remove this guy, and so on. You'll remove the whole path. Then you pick another unmatched vertex, and you are guaranteed to go down all the way, right? And you got two paths like this. Sorry, one here and one there. And that's a maximal set of disjoint minimum length path, because you remove the minimum amount of stuff that was not going to be in a disjoint path. Okay, and this is not maximum, of course. Oops, what happened here? Wow, this hasn't happened to me before, but I think PowerPoint and Apple don't go together somehow. So we found two paths, right? And that's maximal. It's not maximum because, like in this graph, you could have had three paths. But that's NP complete and all that, so we don't want to go there, right? And maximal is all we need, right? Answers your question? Okay, so that's a bipartite case. Really easy. We are done with that. So we go to general graphs. Okay, right away you'll notice one thing, that now vertices have paths of two different parities, unlike before, where you had even and we had odd, right? So if you look at all unmatched vertices and look at the shortest, you can define two kinds of paths, even and odd. And these guys have 3, 4, 5, 6, right? So we're going to define even level as the length of the minimum even length alternating path from an unmatched vertex to V, odd level as the length of the minimum odd length alternating path from an unmatched vertex to V, min level to be the smaller of the two, max level to be the bigger of the two. Is that okay? And why all this will become clear in a moment. Okay, these are needed. And here's one very big difference between bipartite and non-bipartite. In bipartite, minimum length paths are breadth first search honest, in the sense that if I take a minimum length path from F to V, and if U lies on that path, then this is the minimum alternating path from F to U. Okay? Not so in non-bipartite graphs. Why? Because V may sit on the shortest path from F to U with a different parity. So suppose we are looking for an odd length path to V, and V sits with an even parity on the minimum path from F to U, then I cannot take the minimum path from F to U and extend it. It will be self-intersecting. And let me show you an example right away. Yeah, one sec. So what's the odd length path to V? 1, 2, 3, 4, 5, 6, 7. Okay. Here 8. No 9, because this is self-intersect. No 10. Okay. But if you want 9 and 10, if you want odd path to this and even path to this, there are, if you see the rest of the graph. Namely, you go like this. You go to V with an 11 length path, 9 length path, then you can find the even path to A. But not to this guy B. But we can find to B also. If we go to V with an 11 length path, not 7 or 9, then we can find the even path to B. And that's how it looks like. Right? So you have to find a longer path to V and longer path to V to find the shortest path to some other vertices. And this is not just for fun, because this may be the only augmentation. So you have to find the even path to B to augment. Right? And so the bottom line is then you need to find longer and longer paths to V to find the minimum paths to some other vertices. And what does this remind you of? Longer and longer paths. You have to find Anybody? longer and longer. What's the complexity of longest path? NP hard, right? Half longest path, NP hard. So this looks like
You are still, but this is even one path. You want to look at the maximal.
Yeah. I'm just looking at the problem of finding even levels and odd levels, which is sort of a subcase of finding the paths themselves, right? So that's the basic difficulty, that it looks like it should be taking exponential time, forget about linear time, right? And the same ingress is this incredible structure of matchings and minimum length augmenting paths, alternating paths, okay? And the main new message of these two papers of mine is that really a very substantial graph theoretic development is needed. Non-algorithmic development is needed. And many notions and new facts are proofs, new facts, very deep facts are needed. I'll tell you what they are. Not only to give a proof of correctness, but also to state the algorithm in a way that you're not just talking about AND loops and OR loops all the time. You're saying exactly what the algorithm is doing.
So this will be different than your paper with Silvio.
I mean, this is all new, yeah.
The algorithm, not
the algorithm, in effect, is the same, but you can either write it for a computer with do loops and for loops, or say what it is doing through actual graph theoretic structure. I mean, make it possible for human consumption. And so far it has not been, I mean, almost nobody has understood the algorithm. Actually, I realized I was in Moscow this last summer, and somebody from Hashian's old institute mentioned that he had taught it in 1984, which has some Orwellian overtones to it, but as far as I know, he's the only one who had understood it from the original paper. So, but the two authors have understood it from the original. Okay, so here we go. So the whole purpose of the talk is this, and to really show you the algorithm through these graph theoretic ideas. So we first do this alternating breadth first search as if.
Probably one should mention that Edmunds had that algorithm. It was not running in this complexity.
Yeah. This is just about this complexity. So I'm coming to Edmunds in a short moment. So keep doing bipartite breadth first search, okay, marking predecessors as before, until you first encounter such an edge, okay. And the question is, what should you do here? And here we are. You anticipate everything, Avi. So what would Edmunds have done? The great Edmunds who gave the first polynomial time algorithm and had to define P to get it accepted, because they said, okay, there's an algorithm. Find all matchings, take the biggest. So for him, his big idea was to treat this odd alternating cycle as if it was one macro node, okay. Put some nice guy inside it who's going to manage the insides of this node, and tell the outside world, think of me as one node, okay. So all these edges are sitting on top of this node. Find an augmenting path, okay. And wherever it goes into this node, say it goes in here, this little guy will patch up with the correct path. If it goes in here, he'll patch up with the correct path, okay. And of course, this once you have this, you can have another odd cycle and shrink it here, and these can get nested and nested and nested, and very complicated structures can form. But the little guy creates huge simplicity for the outside world. In effect, you are boiling down the non-bipartite graph to a bipartite graph, slowly, okay. Okay, but this will get rid of all the length information. You can't do this if you want shortest augmenting paths. And the right thing to do at this moment is to give the max levels for these vertices, 5s and 6s. And just for these and nothing more. And if you don't, then you will miss such an augmentation, right? Right?
Because to connect that incoming node, you might have to take the long augmentation, right? That's the intuition, or?
Sorry.
You're using the max level here because, if you find an
No. I'm using max level here because that's the only alternating path.
Yeah.
This is not an alternating path.
But if it connects to the node up there,
Then you would take the min level.
the min level, right?
Yeah.
So you
No. You find the augmenting path, but you have to prepare yourself for both eventualities.
So you write down both.
No. All of that has to be done in a very, very super efficient manner. So it takes a lot of things to make that happen. Okay, that's why we have an hour and a half. Otherwise, we'd be done. I mean, with Edmunds, we are done at this point. Oh, that's the whole story. Yeah, we are coming to that whole thing. Yeah, thanks for asking that. But that means you're on top of the game. Okay, so I'm going to call this edge a bridge, and I'm going to call this vertex a base. Okay, in what sense is it the base? Well, if you go back taking predecessors from here, and if you go back taking predecessors from here, this is the bottleneck. You meet here. Okay, and in what sense is this a bridge? Let me define that right away. So I'm going to say that an edge is a prop. An edge UV is a prop, not a prof, but a prop. If U is a predecessor of V, so if U assigns min level to V, so all these edges other than this guy are props, because this assigns min level to this to this, this to this, this to this, and so on. Okay, and any edge that is not a prop will be called a bridge. Any edge. Okay, and it assigns max levels like this one did. Okay, now what happens here? Here, do you see what's happening? We again encounter a bridge because this guy gets his min level from here, this guy from here. And if you look from these two nodes, take predecessors, you do find disjoint paths up to here. So this is not the bottleneck, but this is the bottleneck. So that's the base. Okay? So the base is, in some sense, the highest bottleneck. The highest bottleneck going back from the two endpoints of the bridge following predecessors. Okay? And this bridge gives max levels not only to these guys, but to these guys also. 7 and 8. 7 and 8. So the bridge assigns max levels to everything up to the base, but not the base. Right? Okay, so I will answer your question next. Can you find these structures? Right? And I'm going to call it a quote-unquote blossom now. I'm going to define blossom in a completely non-algorithmic manner in a moment, or maybe in a few moments. Oh, are we getting recorded here?
Yeah.
Excellent. Oh, wow. Okay, that's good for posterity. Yeah. So I'm going to find how to find blossoms, how to find bases, and all that. Okay, and the base is, as I said, the highest bottleneck with respect to predecessors. Okay. Now, one thing to be careful about is when we found this bridge, this was the base, right? When we find this bridge, this is also a bridge because he gets his min level from here, he gets his min level from here. This is also a bridge, right? If we take predecessors down and follow this thing, okay, if we may have to follow this thing many times, and it could be hugely long, there goes our linear time out the window, right? So we don't want to do that. So we want to somehow mark this blossom up so that if we find a predecessor and this vertex is inside this previous blossom, then we jump directly to the base. Okay, so assume that it gets done. Okay, and I'll tell you how to do that in a moment. So if a nested blossom is encountered, skip directly to its base. Okay, and I'm going to show you this new, quote-unquote, new algorithmic procedure of double depth first search that does all this. Okay, and new because nobody knows it yet.
So the difference to Edmunds is that this shrunk blossom is going to have more information that will allow you to go directly to its base. You're still maintaining blossoms.
Yes. But they are the blossoms that are defined through minimum length alternating paths, through these notions of minimum length. Okay, so I'm going to show you this process on a caricature of a graph, a much simpler graph, which is a layered graph. Okay, notice that everything here was layered in some sense. Here, the way I drew this diagram is that I put every vertex at its min level. right? So I'm again going to think about a layered graph in which layers correspond to min levels of vertices, okay? Approximately, okay? Approximately, not completely, because more complicated things can happen. But for now, this is good enough. And A and B are at the highest layer. These are the endpoints of the bridge. And edges can skip layers. Edges go from higher layers to lower layers, but they don't have to go only one layer down. They can go many layers down if needed. And every vertex has a path all the way to the lowest layer, every vertex, okay? And we want to do whatever we wanted to accomplish. And in time, that's linear in the number of edges above the base. These are the edges that we will see, we will traverse on.
So this base defined with respect to this bridge.
Yeah, indeed. Good, yeah. So in this is a layered graph, okay? These are two vertices A and B that were the endpoints of the bridge, and these are edges going down. From each vertex, you can see you can go all the way down to the lowest level layer. So here is how the process goes. There are two coordinated depth first searches starting at A and B, okay? And they try to remain right at the same layer, but of course, you have to make one guy move if they are at the same layer, otherwise they'll be stuck there. So red always has precedence to move, okay? Otherwise, the idea is catch up with the other guy, whoever is lower, okay? So first A moves, red moves, blue moves, red moves, blue moves. They meet. Is this the base? So the convention is blue backtracks first to find something as low as this, if any.
So far it's arbitrary. The choice is whether
always arbitrary. You don't want to look ahead, or you don't want to look ahead and come back, or any such thing. So backtrack anything out of this? No. Backtrack anything out of this? Yes. Continue. They are the same layer, right? Oh, blue went below red. Red continues. They met again. Is there another way to get as low as this? Blue says, let me look first. Convention. Backtracks, nothing out of this. Backtrack, nothing out of this. Backtrack, nothing out of this. He moves here and says, I have backtracked all the way up. I don't want to search above this anymore. All of these vertices are backtracked from. Red says, I'll look for something as low as this. Backtracks, no. Backtracks, yes. They can continue. Red, blue, red, blue. He says, let me look first. Backtracks, no. Backtracks, no. Moves this here. Red says, I'm going to look now. Backtrack to A. His whole backtrack stack is popped. Done. This is the base.
So, but you cannot really implement this for every bridge, right?
We do.
That will
No.
take more than enough time.
Because every edge is traversed once, and once these edges are traversed, these are in a blossom, and next time you just skip over them, right? And we are coming to all of that. So what happens here? Anybody? What has happened here? If for this guy, of course, the base is here. For this guy, where is the base?
Zero.
There's no base.
No base because this
Right. He can go here and he can go here. And there's something better than a base. There's an augmentation. This is what we were looking for, right? The fruit of all the hard labor is here. So we should find this, right? So if no bottleneck, then reach two unmatched vertices with disjoint paths. Okay? So I changed the graph a bit by adding these two extra edges. And at this point, backtrack, nothing out, backtrack, something out, continue, you're done. Okay? So look, we got much more than what we asked for, because we managed to label every vertex either red or blue, and there are two trees here, one red tree and one blue tree, right? And there's a red path from A to every red vertex in the red tree, and a blue path from B to every blue vertex in the blue tree, and a red path from A to the base, and a blue path from B to the base. And of course, here there's a red path from A to the red vertex on the lowest layer, and a blue path from B to the blue vertex in the lowest layer, right? Okay. So, and then the question is, how did we mark blossoms so that we skip them efficiently? Well, when this blossom was found, and I haven't defined a blossom yet, in a moment, I put a blossom node here. It points to the base. All the vertices of the blossom point to this. So when we come down here, we come down directly here. And when this new blossom is formed, it puts down its own node, or it points to its base, and all the vertices point to that blossom node. Agreed?
So who will point to from this blossom, from the old blossom to the new blossom? It's the base.
Only the base. The base is not in the blossom. Yeah. The base is not in the blossom. Yeah. Because it doesn't get its max level from this bridge. Okay. Now we come to some graph theoretic facts. Let's define the tenacity of a vertex to be its even level plus odd level. Okay. So notice 3 plus 6 is 9, 4 plus 5 is 9, and 9 and 9, right? Here, all these green vertices have green tenacity, purple have purple tenacity, which is bigger, yellow have yellow tenacity, which is bigger, and this guy has infinite tenacity right now because his odd level is infinite right now, right? In the graph that is there so far. Okay. Now, this big difference between bipartite and non-bipartite graphs was that you don't have breadth first search honesty. But through the notion of tenacity, we will restore some amount of breadth first search honesty. Okay? Namely, so let's say that with respect to this path P, which is from F to V, and U lies on this path, we'll say that U is breadth first search honest with respect to this path if this length is correct, which means that if this length is even, this is the even level of U. If this length is odd, then this is the odd level of U. Okay? Theorem. If U is of tenacity equal to or greater than that of V, then it will be breadth first search honest on this path. You see that, Avi, why it should be, right? Makes sense. Good, good, good. I don't expect anybody to do proofs now, but if it makes sense, that's all I want, right? So for instance, let's look at the even path to this guy and the odd path to this guy. These are of bigger tenacity, and they are all at breadth first search honest, because this is the even level of this is the odd level of this, and so on. Let's look at the even path to this guy. It goes like this, right? And the vertex that was out of kilter, or I'm using a technical term, that was at a wrong distance, this guy, is a lower tenacity vertex. That's allowed, according to that theorem, right? Okay, now comes a very basic definition, which really that opens up the structure in a very big way. I mean, it really extracts in a very simple way what would otherwise be a very, very complicated story. Okay, so let's see. Let V be a vertex of tenacity. No, I'm fine for now. So let V be a vertex of tenacity T, and let P be a min level path to V or a max level path to V. I don't care which one, any one of them, right? And let HVP be the highest vertex of tenacity bigger than T on this path. So look at vertices of tenacity bigger than T on this path, and pick the highest one. Okay, the one furthest away from the unmatched vertex, and the unmatched vertex will be one of them, of course, because that has the highest, right? So it is this here, it is this here. Okay, look at all these vertices HVP over all the paths, even level and odd level to V. How many vertices did we see in that set? So that's the main theorem, that this set is a singleton.
So again, among all the paths,
Min level and max level, even level and odd level. On each one, look at the highest vertex of tenacity strictly bigger than t, where t is the tenacity of this vertex. Okay, so these crossed vertices. Look,
it's just one path.
I say p be a min level or a max level path. There could be gazillions of them, right? All of them, on all of them, mark out the highest vertex which is of tenacity strictly bigger than t. Just mark them out on each path.
And you say there is just one
There's just one such vertex. And this is a very substantial development. It took, like, I mean, it takes.
And this would be the base of some blossom.
Yes, yes, we'll come to that. Yes, good point. Yeah. Okay, so here, the base of the green vertices is this purple vertex. The base of the purple vertices is this yellow vertex. The base of the yellow vertices is this white vertex, right? And because they're all of higher tenacity than the tenacity of V, they'll be breadth first search honest on all the paths, right? You fine with that? Okay. Now the base of V is this guy. The base of this guy is this guy. So I'm going to call it the base square of V. The base of this guy is this guy, so I'm going to call it the base cube of V. Is that okay, Avi?
Well, I mean, the base was defined with respect to a bridge, not with respect
No,
to a graph.
no. Which bridge? When did I say a bridge?
No, but I thought the base.
No. There's no bridge here.
No, but that, you call this a base of. Initially, you call the base.
Okay.
with
That
respect to a bridge.
right. That was quote unquote base, and you're right. And I'm going to call that later a bud. Okay.
But you change the definition because originally you called base a base for a bridge.
You are right. Actually, now that you say it, base was looking like more.
Was that's the only place where you define the base that
No, I didn't.
was,
Yeah. Okay. Remember I put double quotes on base and double quotes on blossom because I haven't defined those. And very soon.
This is called now a base.
This is called the base. Yeah, you're right. You're absolutely right. I need to make that change in the slides. And what I had defined as blossom before will soon become petal. And the blossom will be the union of petals. And the lowest bud will be the base. There's a lot of horticulture going on here.
No, that's the beauty of Edmunds' painting.
That's the beauty, right? I mean, he started this horticulture tradition in matchings, and we have to keep it going. Okay. Okay, so these iterated bases, I call these iterated bases, base, base square, and so on. Okay. They will always occur on all even level and odd level paths in a breadth first search honest manner. And that's a basic theorem. We'll need it in a very critical way. Okay. Now look at this even level path to B. Right? Remember this even level path to B that went around? Right? Well, V occurs at the wrong distance on this path. It's of a lower tenacity than B. But look what has happened. So I'm telling you that the base, base square, and base cube of V occur on every even level V and odd level V path, right? But I'm going to show you something much bigger, a much bigger statement now. Look at this green marked path. The base, base square, and base cube of V occur on this path as well. This is not a path to V. This is a path to B. V happens to lie on it. V is not even breadth first search honest on this path. And yet all its iterated bases occur on the path. Okay? And here's the theorem. Let B be a useful vertex. B being this thing, a useful vertex. And a useful one is one that lies on a minimum length augmenting path. Let okay, and let V be any vertex on P. then all iterated bases of V occur on P. So the whole path is made up of iterated bases.
That's not what you're saying.
No, I'm not saying that. Yeah, you're right. There could be vertices that are not iterated bases. But every vertex on this path has all its iterated bases on this path, not necessarily consecutively. So you start with base cube, then you see base, then you see base square.
Wait, not necessarily in order.
Not necessarily in order. If this is actually breadth first search honest, then it'll also be in order. But we don't have to be concerned with that. Okay, they occur. Okay, so I can finally define blossom. Okay, so what's blossom? So let B be a vertex of tenacity strictly bigger than T. Okay, then the blossom having base B and tenacity T, I'm going to define as follows recursively. And so let me say one thing. I had defined blossom in my 93 paper, the combinatorica paper, which was different definition than this. But this definition is equivalent to that one, but this is more elementary, and this has given all kinds of new facts, including these, which I never knew before. And they have helped simplify the proof considerably. That's the manner in which the proof got simpler. Okay, just to clarify that. So this is the new definition of blossoms. And here it's always not Edmunds blossoms, but blossoms from the viewpoint of minimum length alternating paths. So this is defined recursively like this. The blossom with base B and tenacity 1 is the empty set. Okay, let ST be all those vertices which are of tenacity T and have base B. Okay, so let me illustrate what ST is. So if you want the blossom, the green blossom with this base, ST is all the vertices with green tenacity and having this guy as base, which is these 4 vertices. Okay, and the blossom of tenacity T and base B is ST union all the little blossoms of smaller tenacity which are sitting on vertices of ST and on B. Okay, so these are the vertices of ST. Are there any little blossoms sitting here? No, forget. So that's the blossom of tenacity green with this base. What's the blossom of tenacity purple with this base? Well, ST now is all purple vertices. What are small blossoms sitting on the purple vertices? It's this one. So the blossom of tenacity purple with this base is green plus purple vertices. The blossom of tenacity yellow with white base is everything but the white vertex. The blossom of tenacity 9 with this base is the green vertices. What's the blossom of tenacity 11 with base B?
Just the purple.
No, green and purple.
Why? I thought the base was not part of the. Oh, okay, I see.
Okay, so that's a totally graph theoretic definition of a blossom. Okay, now let's define the tenacity of an edge. Okay, so a tenacity of an edge for an unmatched edge is take the even level path to U plus the even level path to V and add 1 so that you get a walk, an alternating walk. For an matched edge, it is take the odd level path to U plus the odd level path to V and add 1 so you get another walk. Okay, so it's different for unmatched and matched edges. So here it is for this matched edge, it is odd plus 1, 3 plus 5 plus 1, 9. Here it is 4 plus 4 plus 1, 9. So it's 9, 9, 9, 9, 9. Here also 9. 6 plus 2 plus 1, 9. The green edges are all of green tenacity, purple of purple tenacity, yellow of yellow tenacity. Okay. Now define, and again now I'm going to give you a non-graph theoretic definition, which I'll refine into a graph theoretic definition in a moment. Define the support of a bridge of tenacity T to be all the vertices of tenacity T that are found by doing double depth first search on the bridge. And this is not a, I'm just going to call it definition with 2 quotes right now. Is that okay? So all the vertices that we encounter in the double depth first search of tenacity T, let's define that to be the support. Okay, these are the ones that will get their max level from the bridge. Yeah? Yeah, starting from U and V. Yeah, of course, right? In DDFS from UV. So they get all their max levels from this bridge. Okay. So what's the support of? So in this graph, there are precisely 3 bridges: this, this, and that, and everything else is a prop. The support of this bridge is the green vertices. Support of purple bridge is the purple vertices, and the support of yellow bridge is the yellow vertices. So there are 2 main ideas in the algorithm. One is double depth first search. We've covered that. One is very precise synchronization of events, and we're going to see that in a moment. Okay? And here's the precise synchronization of event. So the algorithm itself is, you best think of it as alternating a breadth first search step and a bunch of double depth first searches. Okay? So at search level I, you search from all vertices having level I, whether it's even or odd, along edges of the right parity, to find min levels of guys that should get their min levels. This is just like bipartite case. Okay? What do you do at after having found all the min levels? Then you look at all bridges of tenacity 2i plus 1, and it has to be 2i plus 1. Okay? And do double depth first search on each one to find their supports and find their max levels.
This is you run from I up.
From 0 on, I equal to 0 on. This is what happens at I. At 0, you look at all unmatched vertices and find level those guys whose odd level is 1, and so on. Okay? So here, 0 finds 1, 1 finds 2, 2 finds 3, 3 finds 4. Aha! At 4, you find this edge, and you realize quickly that it's not a prop. So it's a bridge, and you know it's tenacity already. 4 plus 4 plus 1, 9. So you should do double depth first search on it at what level? 9 minus 1 over 2, 4. Okay. So you do the double depth first search at 4. Okay, and you give max levels to these guys. Okay. And that way, this at search level 6, you can do search on this via the breadth first search step. Okay. Now, this thing is easy to prove because it's just like bipartite. Let's see what it takes to prove the max that all the. So what we want to show is that all max levels having tenacity 2i plus 1 will get their max levels. So sorry, all vertices having tenacity 2i plus 1 will get their max level when we are done with max at this search level. We want to prove that, right? Let's see what it takes. First of all, we have to be sure that every bridge of tenacity 2i plus 1 is found by this search by the end of min, right? So we have to prove that all bridges of tenacity 2i plus 1 have been found here. How do we know that? Well, what about this guy? This is a bridge. I claim its tenacity is 19, 10 plus 8 plus 1. Will it be found before search level 19 minus 1 over 2, which is 9? Yes, because this guy, this 10 will be found at 15 minus 1 over 2, which is 7, and this 8 will be found at 13 minus 1 over 2, which is 6. So we are well in time here, right? Before 9, we found its tenacity. At 9, we will do double depth first search and assign 19 to these guys.
That's not a proof, it's just an example.
Proof coming. But let's see more examples. What about this edge? What do we do about this edge? Useless, right? Like bipartite. Totally useless, because why would you come like this when you can come like this? Good. Not useless anymore. Because you can come and give max levels to these guys or come and give max levels to these guys, right? And so it's a bridge. And its tenacity is 13, 4 plus 8 plus 1. When will we find it? Well, at 5, we'll find this 8. So, and 13 minus 1 over 2 is 6. So we are ready for it at 6. And at 6, when we do double depth first search, we will give max levels 10, 11, and 12. Okay, and now Avi needs a proof, so here's the proof. So the point is that the tenacity of a vertex is always less than or equal to the tenacity of the edge incident at it. So if the tenacity is strictly smaller, then you know it's max level and min level already. If it's equal, and if it's a bridge, then the bridge must use only the min level. So that also you would know, because you're, by the time the min level would be found here, so this bridge would be found by this time.
When it's equal, it's always at the endpoints have the same tenacity.
No. Not both endpoints. No, things like that can happen.
I was asking when an edge, when the tenacity of an edge equals the tenacity of an endpoint.
Yeah. If the two no.
They have the same tenacity, the endpoint.
No, the two endpoints, both of them don't have to have the same tenacity. Like this guy has tenacity 13, right? This guy has tenacity 13. Sorry, this guy has tenacity 13. This guy has tenacity 10, because of or 11. This guy has 11. This has 13. This has 13. But look at this 13. This guy was 13, but we used its min level, not its max level. This guy is, we have used its max level, but then his tenacity is smaller. Okay. So this is okay. So here, what do we have to prove here? So I mean, to prove that every vertex of tenacity 2i plus 1 will be found, okay, we need to prove that all bridges are found and that double depth first search will find the support of all bridges. Okay, take the second statement from me. Okay, that has been proven. Are we done? I mean, if I tell you that all the bridges of tenacity 2i plus 1 will be found, and if I tell you that double depth first search, when you do double depth first search on that each bridge, you will find the support of all these bridges. Have you found the tenacity of all? Have you found all vertices of tenacity 2i plus 1? Have you, or have you not, or is something missing? So I always stop here for a minute, even when I'm running late, and I've never gotten an answer from massively important people. So, and there's certainly one here.
Continue the tradition.
Good.
We're waiting for you
Good.
to tell us.
Good.
Probably the answer is no.
No, we are not done, obviously. So we must show, how do we know? How do we know that every vertex of tenacity 2i plus 1 lies in the support of some bridge of tenacity 2i plus 1? Who told us that? Nobody told us that, right? I mean, this is some procedure that's supposed to give you all vertices of tenacity 2i plus 1. But to prove it correct, you need to show that every vertex lies in the support of some bridge of tenacity 2i plus 1. And that's the main theorem of my two papers, for which this whole development of blossoms is needed. I mean, that whole and all these properties of blossoms are needed precisely to, I mean, for many purposes, but one of the big purposes is to prove this, that on every max level V path, there is a unique bridge of tenacity equal to tenacity of V, and V lies in its support. Okay? So from now on, we can give a totally graph theoretic definition of support. It's all those vertices W which have the same tenacity as UV, and there is a max level path that contains this bridge UV.
So in this case, the other guy, so that so here the tenacity of the vertex is the same as the tenacity.
Yeah.
So on the other side of this edge, the tenacity will necessarily be lower, or can it be higher?
On the other side of which edge? Oh, of UV?
Let's say the W is one of U and V.
Yeah.
Let's say what?
Yeah.
And the other one will be always lower. It
No.
cannot be higher.
No. Oh, cannot be higher.
It cannot be higher.
Yeah. Because tenacity of a vertex is at most the tenacity of the edge, right? Okay. Are supports disjoint? No, because like these two vertices are in the support of both of these bridges. Okay. So double depth first search is done on one of them in an arbitrary order, and what is found is a petal, and this is the bud of the petal. I mean, the two buds. I should probably change this figure so that the two buds are different, have different vertices. Okay, so you create a blossom node, petal node here. When you do double depth first search here, you jump directly here. You don't see these edges again, and this is the second petal, and the blossom is the union of these petals. In general, the blossom is the union of all petals whose bud star, bud of bud, is one particular vertex. Okay, what is this edge? Prop or a bridge? It's a bridge, right? Because he gets his min level from here, he gets his min level from here. It's a bridge, but it's a bridge to nowhere. Empty support. And indeed, if you do double depth first search here, you'll come directly here. You know it says empty support. And so is this guy. He has empty support. And a priori, we have no way of knowing whether bridges will be useful or not. So we have to do double depth first search on all of them, right? Okay, so one more very important question. We found its tenacity at level 5, but we did double depth first search at 6. Question, why not do double depth first search at 5 itself? Right? You know, you have all the information for this edge. 4 plus 8 plus 1, 13. Why not do double depth first search at 5 itself? Why wait till 6? So look here. At 5, we find this guy. At 6, we find that guy. And the tenacity of this is 15. We are ready at 6 to do double depth first search. And we should, right? Why wait till 15 minus 1 over 2, which is 7? Well, do it at 6 and give 15 to all these guys. No harm done. Now I added some more stuff to the graph so that there's a bridge of tenacity 13 there, and these are in that support of that also, right? And both of these are found, these bridges are found at tenacity at 6, search level 6. So suppose you did arbitrarily you did this first, you label these 15, which would be wrong because their tenacity is actually 13 from that bridge. Okay, and you can to an unlabeled guy, you can assign tenacity only if all the lower tenacities have been assigned, and that was not the case here to carry out the inductive proof. And so what should happen is 13 here, blossom here, come directly here, and label only these guys as 15. And that's exactly what I meant by precise synchronization of events. If you do exactly what is given in the algorithm, it'll work like clockwork. If you cut corners, big messes will happen. Okay, how do you skip blossoms efficiently? So here there are nested blossoms, and so you have to come here, and maybe this could be order n deep, and maybe I can make you come down here order n time. And you did order n square work here already. Not very good, right? In skipping these blossoms. Well, so there are two recourses. One is union find. That will add inverse Ackermann function, which we don't, well, it's too big or too small maybe. And the other is to use the RAM model, which assumes that you can do arithmetic on order log n bit numbers in unit time. And so some tables are maintained using that facility. And maybe the constant grows from 4 to 25, I don't know, but it becomes linear time. But the big open question that's in the 1980 paper is still to be solved. Will path compression suffice to do this whole work? Okay, finally, at some tenacity, you find a, you go to two unmatched vertices, okay? And now you have to find a path to this guy, to this blossom. How do you, I mean, you come in here, you're supposed to go up now. You come in as an unmatched vertex, you have to go up to the match. How do you go up? How do you know how to go up? There's a big mess there, as you saw, right? How do you go up and find this path? And the answer is that you not only the blossom node points to the base, but also to the two endpoints of the bridge. And from here, you go, you know you came into the red vertex, so you go to the red endpoint, find the path in the red jungle, red forest, and find a path in the blue forest, skipping other blossoms, okay? And because of these properties that I said, and then find a, patch it all up, all in linear time, remove this path, and then you are left with some half-eaten blossom, right? How do you know that the next path can be found in this half-eaten blossom? Right? Any answer? Well, you don't have to, because remember, the iterated bases of V occur on every even level and odd level path. So when this blossom is removed, this base is removed. And this base was supposed to be used by all the other vertices also. That's the shortest way down. We can remove all those vertices also. The entire half-eaten blossom can be removed. Okay, so what is left is very simple. And you can find the next path there as if nothing happened. And I claim always that this is a simple and natural algorithm. Avi is also laughing at me. No, come on, you understood the whole thing.
I'm joined by other people.
I mean, what could be simpler or more natural than this, given the basic fundamental difficulty, which seemed to make it exponential time, and given the structure that you have to encounter?
Well, I mean, given that it's some years past from it's probably not as simple if so many years
Look,
pass.
simple in the sense that it's not complicated. It's difficult but not complicated.
So did you have this intuition all along? I mean,
No, I spent about 2 years in.
all along. I mean,
No, these definitions are new. So when I
intuition for the correctness of the initial.
no. It was just intuitively clear what's going on. Intuitively, maybe in some very deep part of the brain which couldn't be accessed for many years. No, but I don't. I mean, it really was. I mean, thinking of. I mean, I just started from scratch, right? A decade later, and when the definition of base came, which was after a few months of thinking about it, and then the proof came, then things started falling in shape. And then I had to prove that every max level path has a bridge of the right tenacity, and that took several more things to do. So.
Okay, so since we are asking questions and I see your limo is waiting, I'll ask if there are any more questions so that Vijay can catch his flight.
Yes, sir.
So you said does path compression suffice? Did you mean not using union by rank?
Yes, just path compression. Yeah, and that's a distinct possibility, but at this point, I mean, who knows?
But even using both path compression and union by rank, you still need the inverse Ackermann.
Then you need inverse Ackermann. But the question is, does path compression suffice with a linear time proof? So charge all that path compression. It's extra work on top of what you're doing, just going down, up and down the edges. But can you charge all that extra work to the edges and the vertices out there? And there are tons of edges and vertices to charge it to. Okay, I think there's a distinct possibility it may happen, but it's touch and go at this point. I've been looking at it with another very, very important person from matching. You may know him, Seth Patti. But and so sometimes we go this way and sometimes we go this way. So who knows? It's still open. And of course, we want to say that in inverse Ackermann, right? Right? I mean, factor 4 is too high to pay. Yeah.
Do you think that double depth first search is something that people outside of matching should know about? I mean, is this more of a
I think so. It may have some. I think so. And I think there are more things here. Like in Moscow, when I gave the talk, somebody said, "Why don't you try to embed this in some asymmetric metric space with even going this way and out going this way, and then derive such and such a theorem." I think there's more structural. I mean, there's massive graph theory going on, right? It should have some repercussions somewhere. I mean, it cannot be that this is all sitting in isolation just to prove this algorithm. Could it? It could. Who knows? We never know. Okay, we never know. But I would say it's worthwhile digging around this place, and you might find some more nuggets.